recording. So we've been talking about maximum and minimums, right, of different types of functions. You found them using derivatives, right? You've talked about that already. So we're going to apply that to real world like problems where maximum might be maximum area and minimum might be cost or something or whatever, or maybe like minimizing waste or material. It can be anything when it comes to optimization. But there,
Wow, this really came at one hell of a time for me.
so it's pretty neat, and so you can use that for as long as you have your dimensions and whatnot. You can do all kinds of stuff by using the derivatives. So let's get started here.
Oh, I think I want to do it. Well, actually, here's the thing: we're putting up siding on a building, so it's like,
Oh yeah,
so it's like, yeah. I was just informed of that 2 days ago.
that sounds like you're gonna be busy, huh?
Oh, you have no idea, especially after everything is broken this weekend.
Ugh. I'm sorry, man.
Whatever. The two biggest things was I had a fish eat the bobber off my pole, and my uncle succeeded in breaking the hydraulic system on some of the machinery.
Your uncle broke it?
Well, it's his machinery at the very least, but yeah, he broke it.
Hmm. Well, at least it was his and not yours, right?
Might as well just call it ours. I mean, I do almost all the maintenance on it anyway.
Hmm. All right, so finding the length and width of a rectangle that has a given perimeter and a maximum area. In the book, there's a lot of cool examples about building fences and whatnot that are pretty common problems. But the homework will start off with just general perimeter and maximum area. So find length and width of a rectangle given this perimeter. Given this perimeter, 380 from the homework, 380 meters. So maximize the perimeter. I'm sorry, maximize the area, knowing that this is the max perimeter that you can create, right? So basically, the idea is like you're drawing a rectangle, right? We don't know what dimensions these sides, the width and length should be. I do know that the total distance around has to be 380. So let's say you're trying to create like a fence to enclose something, but you want to make this space as big as possible. So with this restriction, what is the length and width that will maximize the area? So that's what the 4.7 will be about. Will be these types of questions. Okay. So it's going to help to know or look up the perimeter formulas, area formulas, etc. All right. So um, I don't know. We can call in the problem. I think they call let length be x. Let width be y. All right. And then let's see here. So where should the x go?
On the width.
All right. So x is length. So where do I put it? Here or there?
Oh,
First one.
that's in the bottom.
Bottom, right?
Ahora.
And then the y will be here, correct?
Yes. Uh-huh.
So knowing that, you can kind of already create your perimeter formula, right? Perimeter P
Equals 2L plus 2W.
Well, we call L and Y All right, let's use our variables here. You're
Yeah,
not, you're
my
not
bad.
wrong. You're not wrong though.
Yeah, sorry, recall. So 2y and 2x.
Yeah, there you go. Well, we couldn't use the other one, but we're using this just
Oh.
because we're used to dx,
Yeah.
dy, and dy dx, because that's going to come up in a
Mhm.
second.
Okay.
So we have two sides added together, two more sides added together. That's the total perimeter, and that has to equal to 380 meters, right?
Mhm.
Now, area, which we'll call A, is equal to, what is the area of a rectangle?
The area is
X times Y.
Yeah, right, just x times y, the length times the width.
mhm.
Okay. All right. Now, if I were to solve for y in this equation, what would y be equal to? I'm going to do this just because we may need to substitute. Using perimeter, solve for y, and then we can look for dy dx. That's why I'm doing this. Oops. Solve for y. So here we go. 2y plus 2x equals 380 meters. Subtract. We can go ahead and divide it by 2 right now, I suppose. Everything by 2 would give us y plus x equals, what's half of 380? That one
Divided by
by 2,
190.
right? If we divide everything by 2, right? 2,
Mhm.
2, 2 gives me this equation. Solve for y, we get 190 meters minus x. Okay.
Mhm.
All right, so I'm going to use this in a minute. So now we can plug that into here and get one equation in one variable instead of two, right? Instead of doing an implicit derivative, we can just sort of replace the y with this x. Or sorry, replace this y with the 190 minus x. You see where I'm going with this?
Yeah.
So plug this into area equation. All right, so we get a equal to x times y, which would be a equal to x times 190 minus x, right? Which implies that the area equation is equal to 190x minus x squared. You guys still with me to this point?
Yes.
Mhm.
All right, I skipped a little bit of algebra here. So what are we trying to maximize? All right, let's not get lost to what the heck we're doing.
We're trying to
Yeah.
maximize A.
Right, the area, right? A. So, and we've learned from the last couple of sections that we need to take a derivative and set equal to 0 to find the critical points, and then one of those may be a maximum or minimum. Once we find the x value that creates the max, that will be your length. Then you'll plug that guy into here, which will give you your width, right? You see where we're headed?
Somewhat.
So take a derivative. Derivative of a and set it to 0 to find the max. Well, I guess I should use the word critical numbers.
You said take the derivative of a.
Yeah, with respect to x.
Is that what those? Sorry, I'm trying to read. beginning
Yes. Where we're at? Here?
of below that.
Oh,
Yeah, take a
take a
derivative.
derivative of a and set it to 0.
Oh, okay. Sorry, I
Yes.
can. Yeah.
No, it's okay. Maybe I wrote too fast there. I'll try to be a little more neat. To find the critical numbers. Okay, so find dA dx. So what is dA dx equal to?
The derivative of d over dx, and then
190 minus 2x.
Yeah. So set this guy to 0. That would be 190 minus 2x equal to 0, which would give us x equal to what?
95.
95. So this is our possible maximum or minimum. Most likely it is our max because this is a parabola. We should probably only have one critical value, which is the max or minimum. So we should be good at this point. To test it, you could plug it into the second derivative. But notice, what would happen if I took another derivative?
Mm,
It would just give us a whole number.
Right, it'd give you -2, right? So, and it makes sense if you think about it. There'd be d second derivative of x would be -2, right?
Mm-hmm.
This is always negative, no matter what x I choose, correct? It's a constant. So, what does the second derivative tell you before we point this out?
The inflection points.
Yeah, it does help us find inflection points. Here we clearly don't have one, right? First derivative tells us about increasing and decreasing. Second tells us about concavity, right? So we said that if you plug in an x and it's negative, you have concave down. But it's always negative, which means this function is always concave down, which makes sense, right? What does the graph look like? Let's go find it.
There's no picture on this problem.
Yeah, let's go graph it. Right, so this has all the ideas coming up, I guess, in the background here. I'm just going to call it f of x just to be simple. Way up here somewhere. Jeebus. There it is. 95. There's our peak of our weirdo parabola. 95 comma whatever. 90, 25. Double check that I plug this in right.
9,025.
But anyway, this is an area function, right? This is not telling me anything about the width. But this is showing me what the maximum x is. In this case, we were using x as length. So this confirms for sure that and also the second derivative tells us that it's always concave down. We have one critical value, so it has to be a maximum. All right, so I'm out of space on this page. So let me write the width equation here. We had y equals 190 minus This pen dying on me already. 190 minus 2x. Oops. Okay. So there is my width. Let me switch pens. And we found x to be 95, right?
Mm-hmm.
So that's my width. Plug that in, and you'll find your length. I'm sorry, this is length, wasn't it? Shoot. So y would be equal to 190 minus 95. So what is my width?
One nine. See, 190 was the width. I thought we already did that. Oh wait. Should be 90. Actually, should be 90. Well, yeah. Should be 100 and something. No, wait.
95.
Yeah, I'll say that. Wasn't that just?
Let me double check everything.
I was like deja vu for a sec. I thought we already did
Yeah,
determine
it
that.
made me doubt my answer too. But in this case, they are equal. It doesn't always happen, but whatever. Turns out when the length and width are the same, with our restricted perimeter, we will have the maximized area. And that maximized area was what, like 9,000 something on the graph, right?
Yep.
Forgot what it was already. Yeah.
I want to say 9,026.
I mean, they didn't ask for it, but there it is,
Oh,
right?
25.
So to create, I'll just write it down, a max area of 9,025 meters squared with a perimeter what was a perimeter?
300 and something.
380. We need a length and width of 95 meters. And they didn't ask for that explanation at the end, but just to put it all together in our heads, what was going on, and that's what happened. Is there any questions about any of the steps? Does the idea make sense or no?
Think so.
Can you go back to the other page, please?
Yeah. Any questions on this page?
All looks pretty clear. Over there, that's fine over there.
Okay. Let's do one
What is the-
more, and then we'll move on to the review.
Which homework did you pick off again?
So I took out 4.8, I think.
Oh, okay. I don't know if I.
Okay.
So let's see, we split it in two. We assigned one number. We found the derivative. And then we took second derivative.
Your second confirmed that it was a maximum, but so did the graph. So you could have verified with the graph. But the second derivative pretty much says, you know what? It's always concave down. So there's only one maximum. And
Okay,
we
where
have-
did the 95 come from out of again?
Solving for x here. You take
Okay.
the derivative, set it to 0, solve for x. That will give you the best length.
But could that give us our minimum too?
Yeah, the approach for finding a minimum, like if they were telling you to minimize the area or minimize the profit or cost or whatever the heck you're talking about, you would take the same approach. It's just that your equations would be different. So it'll still be derivative equal to 0 because those critical numbers could be a max or a minimum, right? Whether it's a max or a minimum depends on the function itself, which is this guy. This determined that we're going to have a max. This basically proved it here. This found the location. All right, let's do another one. Probably need a. Man, I'm out of paper. Yeah, that's fine. Maybe I can put it down here. That's fine. Nah. Okay, sorry. All right, so this one says example 2. Find the length and width that has given has the given area and a minimum perimeter. So this one's kind of like the opposite of what we just did, but the procedure will be exactly the same. So they're giving us an area of 25 squared feet. Okay. So all the information we're given, which means we have to know the formulas, right? We know that area is equal to A, which is equal to X times Y. Perimeter is P equal to 2X plus 2Y. And we said X was length, right?
Mm-hmm.
Y was width. Okay. Right, so we want us to minimize perimeter. So we're going to have to get this into one variable. That way it's not too complicated. And we're going to have to solve for x on this guy since we have the 25 feet. So solve for x on the area equation. Right, so that would give us x times y equal to 25 feet squared, right? So solve for x, that would be equal to 25 feet squared divided by y, right?
Mhm.
So plug this guy. Oops, sorry. I think last time we solved for y. Let's stay consistent. This is not wrong.
Actually, no, we ended up swapping our variables, so it does. So I really don't think it matters. Last time we used y for length.
No, last time was x was length still.
Oh, okay, my bad.
Okay, but yeah, the process is very similar. All right, so solve for y. Not that it matters. I just wanted to stay consistent.
Mhm.
So y is equal to 25 feet squared over x. So changing this note. Solve for y. Okay. So plug this into the perimeter equation. And find the minimum. That's what we're doing here. Okay, so we got P equal to 2x plus 2y, which is actually now 25 over x. Right? Okay, so dp dx would be equal to, what is the derivative going to be? I'll do the hard part for you. It's going to be 2 minus I believe is this. Is that what you guys got?
Just a minute, I'm still crunching numbers.
Take a second one. Yeah, double check me.
Yeah, that's what I got.
So negative 100 over x cubed. Second derivative would be this guy.
But hang on, I didn't get the 2. I only got negative 50x squared.
That's fine. All right, so set this to 0. Solve for x, and see where the critical points are. Right. So 2 minus 50 over x squared equals 0. So that'd be 2x squared minus 50 over x squared equal to 0.
Hang on, actually, I do think we made a mistake, Jack.
Where?
I just realized that I was solving for, I swapped out my y and my x values before I started. So I was solving for 2y plus 2x, and I corrected myself and went back to 2x plus 2y, and now I have an extra 2 added onto this. So, oh no, yeah, we did get it right. So that 2 that was there, that's where it came from.
This one, right?
Yep.
Okay.
I wrote it. I just wrote it backwards. Okay.
No, you're
Okay. Sorry, I got lost for a second there.
good, man. Okay. One moment. Okay. So what are the critical values? Can you tell by looking at it? What makes the top part 0?
Say that again. Sorry.
What is x?
5.
Yeah, for sure, right? It's gonna be 5, and what else? -5, right?
Yeah. But since it has like a it's divided by x squared, doesn't that mean that there will be asymptotes?
The graph will have asymptotes, the original, and so will the derivative. The question is this guy going to be a critical number? And usually it is, but if I can't plug it into the original, then it's not a point of interest at all.
Okay.
Like if this appeared only on the second, only on the derivative, but not the original, which is up here, right? Where is it? Here. So like even if it was a critical number, I can't plug it back in here to check if it's a minimum or max or whatever, or find the location. All right. Anyway, so we got 2 possible places for this function. All right. Which one do you think can clearly be ruled out? Because what does x represent?
-5.
The length of a rectangle or square.
Right. So negative length makes no sense, does it? So I don't really care about that guy.
I'm sure in some physicist's mind somewhere it does.
Yeah.
This one's looking for two values.
Right. Right now we're only finding one though.
Okay.
Right. What is x? What are we looking for here? Right. We just said it was length. We still need the width. I don't know why I wrote perimeter up here.
So yeah, that confused me too.
We still need the width. Okay. So let's see here. If I plug that into here, do you agree that's going to be negative? The output.
Is that x cubed?
Yeah, it's x cubed. Oops, actually, that should be positive. Sorry about that. Second derivative will be 100 over x cubed. Double check here. -2. Well, yeah. Anyway, since this is positive, and I plug in a positive, it will stay positive, right? Do you agree with that logic?
Yes.
Right, so meaning if I were to plug in 5, it would show me that it's concave up, which is a minimum. Right, so since the second derivative over dx squared at 5 is greater than 0, then we have a minimum at x equal to 5. I don't know what the y is, but at 5. Now let's graph it to verify our idea here. Do you have any questions so far, though?
Not so far.
Okay. So our equation was p or y, whatever you want to call it, f of x equal to 2x plus 25 over x. Let's see how strange this looks. Okay.
Holy Lola.
So there's our function. We have two extremas. Make sure I wrote everything correctly. Oh, that should be 50, right? Not 25. Wait, no. Yeah, 50. There we go. Now it makes sense. So you see how we have a -5? So that was a critical value. There's the other one. But we disregarded this guy because we're not worried about, we're optimizing something, which means it exists in reality. So 5 for our length is what we want. Okay. Does this make sense how we're applying these ideas of maximum and minimums to actual problems?
For the most part.
So the theory is the same that we did in the last 3 sections, but now we're using it on like a box or a fence or whatever. Right? Or if you have like a sheet metal or some piece of steel and you don't want to waste too much, you can decide how much you should cut in certain areas or whatever. If you're trying to make a metal box, how much sheet metal should you cut? You can all figure that out with minimization.
This is actually something I'll find myself using on a daily basis, no matter what. So
Yeah, so you can just figure out the equations for the shape, minimize it, and you'll have an idea as how to cut it. Okay, I don't think I have space there. Well, that's fine. Just put it here. So that was my length, right? So width is going to be, I'm just kind of right with these weird pens yet. Width will be y, which is equal to 25 over x, which will be the same this time. I guess these first 2 questions are not too difficult. Excuse me.
in your examples,
Yeah. I think it was in feet. Just double checking. Okay.
Yeah, it's in feet. It's
Anyway.
square feet. But yeah.
All right, guys. Any questions on this? The idea behind optimization.
No.
All right. So when you go through the homework, you have a few. I think number 3, 4, and 5. They're just giving you a function to minimize or maximize. But then after that, they get back to a rectangular shape or whatever, a solid shape. Maybe minimize volume instead of area.
Yeah.
But the idea will be exactly the same. You just have different functions, and the numbers will be different, right? The theory is the same. Okay, let's see here. Oh, I didn't realize that. All right, I didn't realize I did. I opened the homework for. I don't know if you could see it or not, but it's open now. 4, 7, 4, 8. That's the ones I'm removing. 4, 8. 5, 6 apparently is on this test. I forgot about that. Okay.
Is that the median one?
Intermediate forms.
Yeah, intermediate, indeterminate. Sorry.
Or my bad, yeah, indeterminate. My bad, I misread it.
No, it's okay. It looks like it, right?
Uh-huh.
All right, so let's take a short break. It's 9:53. Let's come back at 10, and we'll finish the indeterminate forms.
Jack, can you help me out with an optimization?
All right. So, do you remember when you were doing limits? You had different techniques. You'd had the factoring, and see if stuff would cancel, and then you'd plug in the value and see if it would work, right? Then you would also try plugging in values really close to the x you're talking about from both directions and see if it's the same. And if it was, then you say the limit exists. If they were different from both directions, you'd say it doesn't exist because of that reason. That's the requirement and definition. But if you were to get a situation where you get 0 over 0 or infinity over infinity, then that's considered to be an indeterminate form. So you can take derivatives of the top and bottom separately as if they were two different functions, not doing a quotient rule, just something different. That will let you take another attempt at the limit, and if it works at that point, then you're good. So let me show you what I'm talking about. It's a 5.6 indeterminate forms. Okay. And L'Hopital's rule. I believe this is some French guy. When I first read the book, I thought it said El Hospital, but it doesn't.
That sounds French. Well, that's the weird thing about French is you typically don't know what it is until you've heard it spoken out loud.
Yeah, I always struggle with the French language. It's not my thing.
At least it still shares the same roots with English.
All right. So let me grab the book in case there's a theorem we might need. 5.6. I don't think we need anything special, but it's all right. Yeah, I think we're good. Okay. All right, so let me put this in plain English, I guess. So suppose.
I'll put it in French. How's that sound?
Oh, thanks. g of x has, well, I forgot to write the limit part. Suppose the limit as x approaches, I don't know, we'll just call it infinity, of f over g, and f prime g prime exists if the limit is equal to negative infinity over infinity, or sorry, infinity over infinity, or 0 over 0, then this is an indeterminate form. Indeterminate form. Okay. Well, actually, I'm going to cross out the then because I'm going to use it in a second. Put this in parentheses here. This is a side note. So then, if that happens, you can do this. So the limit as x approaches infinity of f over g will be equal to the limit as x approaches infinity of f prime x over g prime x. So this is basic. That is your L'Hopital's rule right here. So what it's telling you is if you end up with something like this, infinity over infinity, 0 over 0, then you can take the derivative of the top and bottom separately, and then try to take the limit again. And if you get another indeterminate form, you could take another derivative and try it once more until you finally get a limit, which is kind of neat. So that's L'Hopital's. So we're going to use that when necessary. Okay. It's not always necessary. So some of these examples, you can use your old techniques from chapter 2 and see what happens. So example, so here's example 2 from your homework or homework problem 2. Evaluate the limit using L'Hospital if necessary. Whatever. Okay. So here's a function they give us. So the limit as x approaches 0 of let's see here, square root of 4 minus x squared minus 2 over x. If I plug in 0, what do I get? Do I get an indeterminate form?
Yes.
Right? This limit is equal to 0 over 0 is indeterminate, which means we can use L'Hopital to help us out. So this would be equal to the limit as x approaches. I'm going to put a little symbol here that I did L'Hopital. What is the derivative at the bottom? Just the x.
1.
1, right? Derivative at the top is a little more complicated. So this will be 0, right? But this will be a chain rule. That will be 1/2 4 minus x squared negative half times 2x, right? Halves and twos are going to cancel. So the limit as x approaches 0 I can bring that down, right? So that would be the square root. That x stays 4 minus x squared. What is this? Can I take the limit now? If I plug in 0 here and 0 there, what do I get?
0.
Yeah, right? It's going to be 0 over square root 4, which is 0. So we do have a limit after all. Do you see how this works? Or the idea here?
Yes.
So back in chapter 2, when you had something like this, you had to multiply by the conjugate, right? Do you remember that?
Yeah.
So sometimes you can get away with not doing all that nonsense, but only if you have an indeterminate form. So if you see something weird like this, that's not 0. So you gotta go apply L'Hopital. Then you get to here. If you had infinity over infinity, let's say this is going to infinity, then you would have that case, right? Assuming they were the same degree and nothing else happened, but whatever, you would have indeterminate. Any questions about this example?
So what's the difference between the L'Hopital, like the original limit and expression, and then the final it's called stage we got to? Sorry, I'm just trying to see
No,
the difference.
so when you have indeterminate form, there's a theorem that says that the limit of that quotient is equal to the limit of the derivative quotient. So they are equal, meaning if I can't take this limit, I can take this one instead. That's what we did.
Okay.
So this was not cooperating, so we did L'Hopital. This limit was easy. We got a 0. Does that make sense to everybody? Any questions?
That makes sense.
Okay. Let's see here. Yeah, let's do another one. This is number 4 from your homework. So same question, evaluate the limit, use L'Hopital if needed. All right. So the limit as x approaches 1 yeah, sorry, you know what? Something's been bugging me this whole time. This right here needs to be more general. It's not just infinity, it's to any value c. I don't want you to feel restricted. L'Hopital says anything is cool. Okay. All right. Alrighty. So next question is number 4. When x approaches 1 over x to the 7 minus 1 over x to the 23rd minus 1. All right, so if you plug in 1, if you take the limit, what happens?
Goes
It
to
goes
zero.
to 0.
Yeah, it looks like we get 0 on the top, right? 0 on the bottom. It's indeterminate. So therefore, we must do L'Hopital. So that's going to be derivative of the top separately. Remember, this the only time you do that is with L'Hopital, right? Any other time you have to do quotient rule. You see what I'm saying? Don't get used to this.
So unless they specify.
Yeah, if I told you to take a derivative of this function here, you would do it like normal. But if you're asked to do L'Hopital, well, then you do the derivative of the top and bottom separately, assuming you have an indeterminate form. That's the only time you do this. Okay. So there's my limit. Now if I plug in the 1 and take the limit, what do we get?
7 over 23.
Yeah. 7 over 23. So now the limit exists. So not too bad, right? All right. The rest will be similar. They'll have different questions or different functions. We might have an e to the x or something like that come up, but it'll be the same deal. Guys have any questions about this idea? I think see if I can do one more. Maybe we did 2. Yeah, do one more.
I did have a question on the concave, like upward and downward.
Uh-huh.
I was wondering if there was like a shorter way to do it, or
The shorter way to know if it's concave up or down?
yeah.
No, it has to be the second derivative. The other way would, I mean, is the question only asking for concave, right? That's what you said?
Yeah, upward and downward.
I mean, you could do the first derivative test, but usually that's more work.
Yeah.
Unless the derivative is really difficult.
Well,
Then
it was like with whenever they're divided, it would take me longer.
yeah. So if the derivative is a pain, then maybe do the first derivative test. That way you don't have to do 2 derivatives. If the derivative is easy, then stick with the second derivative test to find out about concavity.
Okay.
Okay. Yeah, ready? Let's do another one. This time with this example. I don't know what it is. Let me see. Number 8. So same question. I'm going to put quotes here so you know it's the same deal. The limit as x approaches infinity of x cubed over e to the x squared. Do you agree that this is an indeterminate form of infinity over infinity?
Yes.
It looks like the bottom should grow faster. The answer should be 0 just by looking at this rate Visitor rate is really fast. But to prove that, we can do L'Hopital and show how why it's going to go to 0. So let's do the L'Hopital here. Some French stuff, I guess. The x approaching infinity. The derivative of the top is not too bad, right? Derivative of the bottom, what's that going to be?
Two x e to the x squared.
Yeah, 2x e to the x squared. Okay. So that will cancel one of the x's, right? So now I have the limit as x approaches infinity of 3x over 2e to the x squared. But you see how this is still indeterminate. So do it again. So that'll be the limit. So the top will just simply be a 3 over 2 times 2x squared. Oh, sorry. E to the x squared. Right? Yeah. So now what is this limit?
Zero.
Yeah, it has to be 0, right? There's nothing on the top. Bottom grows infinitely fast. Fraction goes to 0. Is there any questions about this problem? See, we had to do L'Hopital twice here.
Makes sense.
Why did a x disappear?
Oh,
So I'm just
we did
yeah.
the derivative of the top, right? What is the derivative of 3x?
So you got the second derivative?
Yeah, we did it one more time. So we
Oh,
did it.
okay.
We did it once. And it was still indeterminate, right?
Mm-hmm.
We did it again, and then it was no longer indeterminate. It was simply 0.
Yeah. Okay. All right. Thank you.
Yeah. So just do it as many times as you need to, assuming you still have an indeterminate form. You are not able to do it if you do not have a 0 over 0 or infinity over infinity. All right. All right, guys. I guess we'll stop here. You guys have any questions from?
I do have one from 4-7. Oh. Problem number 2. I want.
So test 3 is the majority of is mainly chapter 4 and 5.6. I will remove the 4.8 stuff. But yeah, there will be a test 4, which is over 4 sections of chapter 5. Okay. So yeah, prepare for the 21st, and we'll review it next time. You guys have any questions about what we just covered? If not, I'm gonna do that homework problem.
How would we so the answer for this whole thing was 0?
Right.
Okay.
So you would just input 0 to the homework, but on the test you'd have to show all this stuff.
Okay. All right. Thank you. Thank you, Professor. Appreciate it.
No worries.
Have a nice night, everyone.
Have a good night.
See ya.
Thanks. See you.
See you later. All right, you said 4-7, right?
Yep, problem number 2. I just want to know how to, what it wants me to enter exactly.
I want you to find the length and width. So you're gonna, it's the
Page
same as the last one. It's just that they
Uh-huh.
did. Oh, hold on, let me double check.
Just, yeah, I think I found it.
So yeah, you just plug in the smaller value first. So if the length is or width is smaller, plug in that first. If they're the same,
Well,
then just
yeah,
put in both.
Okay. Okay, so where the hell did I screw up
Y'all have a
at?
good one.
Yeah, good night, man.
Because let's see, I think I did this right. I'm pretty sure. Follow the steps. Can you help me through this? It's 36 is the value
Oh, you have 36 for
Mhm.
area or for what?
for area, square foot.
Should be 6 by 6.
Okay, that's where I went wrong. Oh, okay, I see where I went wrong. Yeah, I did it right. But I found a different I found a different formula.
Mm.
I was doing it for I did an extra multiplication that I shouldn't have done.
It's all good. I'll send out the notes in a second.
Yeah. Okay.